Good morning. How are you? Today we will just think about the relation wise dimensional modeling. So the agenda is we need to know at a conceptual level what's about. Let me take an order transaction as an example here and how the order transactions is converted into a dimensional model. If you look at this picture, the order transaction as list of columns. By looking at this, you can see order name, customer ID, customer name, customer first name, order total amount, and order date. So as we know, when you're converting the transactions, let's say relation database into dimensional model, we need to know about two things. One with this called a dimension, another with this called fact table. The factor which hold your matrices, not only that, it also hold the key items and that point to the dimension. The dimension will have the textual values and it has its own the primary key. You can see with the dimension customer ID is a primary key, and with order date key is a primary key, and all these dimensions relations have a relationship with order facts here. So the fact tables is nothing but a combination of primary key from the dimension plus your matrices. Your matrices are a number, order number, net order amount, and a payment order amount, and order total amount, or the discount amount, or the four matrices which hold your numeric data. So this is like a simple dimension model. We can go to the next slide. Here we can see sales data mart, where it records all the transactions with sales by customer, by product, by date, and the respective locations. And you can see a purchase data mart. It has the facts which is involved on the cost incurred by vendor, by product, by date, and employee. And if you merge sales data mart and purchasing data mart, then you can see the enterprise data mart. The advantage is that if you see in a holistic way, the sales data mart it's only deals with the facts, the measures about sales, and the purchase will only deals about the purchase. If you want to have a consolidated view, a kind of a data mart that will address your sales with cost together and do a kind of reporting your sales and cost with this dimension that involves your enterprise data warehouse. And you can see there are common dimensions between these fact tables are the product dimension and the date dimension, which is a kind of a bridge between the two fact tables. And the customer dimension and the location dimension are specific to the sales, and the vendor dimension and employee are specific to cost. Through these common dimensions, and the sales can be interact with each other, and we can create a consolidated report with all these dimensions and facts here. And we can go ahead with this snowflake schema. You can see the sales is a fact table and it has its dimensions are time, channel, and you can see customer and product. It's look like a star schema if you exclude the supplier and the countries. So by default, the star schema is a dimensional fact model and it is a denormalized. If either any of your dimension, which is again further normalized, then that tells about the star is extending to the one more level. One more level here, I mean, the product is an extension to another dimension supplier. Same with the customer extended to the countries where they belong to. So this is a typical example of your snowflake schema. And this view will give a kind of a picturizations how a relationship via dimensional model. The same like if you look or picturize your relation model, it has a conceptual model, logical model, physical model. The conceptual model start with identifying your name of your table and your column. The logical model will give you the furthermore detail of your conceptual model with detailed out all your columns. May or may not you can identify the data type. On the physical model, it is an extension of your logical model. What it identifies among this, you need to identify the primary key, the foreign key, and the data type, and your constraints, everything to identify here. On the flip flop, if you look into the dimension modeling, we segregate all this to a denormalized structure, the dimension fact model. You can see here. And there is a theorem which is called CAP that we need to know what about it. It's all tell about how the data to be followed, adhere with this the thing actually. As we know that C for the consistency and A for the availability and P for the partition tolerance. Let's tell about and also it involves the type of database what it follows this the theorem cap, and this is a typical picture that will tell about the relationship between OLTP voice OLAP. So at the information we call it a data. From data we are doing a OLTP with the tables which related with the kind of a summary to detail table. With the dimensional model, we are related with dimension and fact. So if you look at the data, when you look at OLTP, it is rows and column. When you look at the dimensional model, it is nothing but dimension and fact table, where dimension hold the textual value and the fact hold your number plus the key items that associate with the respective dimension. And the relationship, you can see the dimensional model one to one to many, m to one, and m to m. So when you're supposed to have a dimensional M2M, then you need to make it a kind of a bridge table between the fact tables. Let's say you can avoid this M2M relationship always. It is best recommended. So if you look at the normalization, the OLTP is purely 100% normalized, and the OLAP, which is nothing but dimension fact table, it is a denormalized one. And again, there are three model we can say in OLAP, which is star schema and snowflake schema and the galaxy schema. You can see on the fourth line item, on the star schema, it's a purely a denormalized one. On the snowflake schema, it is not like as a completely denormalized. Either any one of the dimension may normalize. That's what we. It's a both a combination of normalize and denormalize. That's why we call it as a snowflake schema, which is again an extension of star schema. And the multi schema is again a purely denormalized one. So we need to know about two things. Yeah, schema, if you have a collection of multi-star schema, then that is called multi-star schema. And What are the issues that we may encounter during the dimensional fact tables are those traps, loops, and Cartesians, and data type that need to be identified. If there is, you have M-to-M relationship, multiple fact tables. If you want to connect it, you need to make a bridge table and do that. And if you look at the giants, when regard with the OLTP, it has more join with a normalized one. And when you look at from a dimensional model, it is always a lesser join because all your dimension pointing to the fact table. And with regard to the performance, based on the number of joins that you need to think about it, how far the join actually. In terms of the performance, the star would be always the recommended one, and it is better. And when compared with Snowflake, it is lesser than the star schema, and multi-star schema would be the better one. I think these topics that we have seen is a better understanding between OLAP and OLTP and gives a better visualization. Thank you.